So you were very successful in our do now, drawing a hydrogen bond, and that will be important when your quiz rolls around. So make sure you're comfortable with it. We're going to continue with the learning goal that's really been essentially our whole second quarter's worth. So this is big idea 2, and what our focus is going to be on today is the forces that exist between molecules that help you understand properties of liquids and solids, and especially their transitions between one state to another. So we're going to review again why stronger IMFs result in higher melting and boiling points, and you'll see the link to vapor pressure today as well. There's a lot of review in today's lesson for those of you who did quite a bit with thermo last year. If you didn't, it won't be terribly overwhelming. It's really pretty straightforward, and we'll work through that aspect of it. We're going to pick up with phase changes today, and you'll see that changes in phase very much linked to intermolecular forces. Those phase changes, which are examples, of course, of physical changes, are listed on the board. I don't really like to memorize a lot of different things. I'm very picture-oriented, so I really need some type of visual to understand my phase changes. Let's take a look. For example, the transition from solid to liquid is known as what? Melting. And the transition from liquid to gas is known as boiling or vaporizing. If you go gas to liquid, you are and if you go liquid to solid, just for you. If you go directly from solid to gas, that's sublimation or subliming. And if you go from gas to solid, that would be deposition or deposing, and this is your snowflake generation right there. Subliming, iodine sublimes, we'll take a look at that, or like the plug-in air fresheners, you have a solid that then give off that gaseous pew-pew. All right, now let's think about this. As you go in this direction, these processes along this direction from solid to liquid or liquid to gas are going to be endothermic. And I like to just think of it as men. Just trying to think how to phrase this in today's day and age. But let's say that, girls, your boyfriend gives you a nice stuffed animal or a bouquet of roses or whatever. It will melt Your heart melting is endothermic. So if you can remember it, awesome. The light bulb has gone off. I'm just teasing.
Oh.
What's endothermic?
Wait.
Are you
Can't
you just tell me it's getting hotter?
Is it getting hotter?
Yeah.
Okay.
So if it's melting, it's getting hotter. And
Men get
You're
hotter.
absorbing. This is going to go in the wrong way. You're absorbing energy. Alrighty.
I mean, you can think of it.
That's definitely not what
Wait,
it
how would you explain it if before? You didn't get to think about it.
Oh no, I just was trying to be politically correct.
Last time.
In November of 2017. In this direction, exothermic, and delta H is negative.
Do you have anything for that?
Absolutely, and I'll tell you at the break. This is the release of heat. Very important to know endo versus exo. We'll get into it more in our chapter on thermo, but you've got to know solid to liquid, liquid to gas is endo, and in the reverse direction it's exo. Also, if you're comparing the orderliness of a state, which has more order, solid or gas? Solid for sure. So as you go in this direction, you get more disordered. As you go in this direction, you get more ordered. Think back to honors for some of you. What is a measure of disorder in a system called? Entropy. All right, so this is enthalpy, the other is entropy. And we'll get into entropy in our thermo chapter when we open up the third 9 weeks. Questions here?
Are we going to do the KEQ thing again?
Yes. All right. So this one diagram puts a tremendous amount into perspective, and I think it will help you a lot in regard to phase changes. You also want to understand phase changes in regard to IMFs. Much greater IMFs in a solid than in a gas. So as you go in this direction, IMFs are breaking up. As you go in this direction, IMFs are forming. We typically say 3 states of matter, solid, liquid, and gas. Sometimes we refer to gas as vapor. We use the term vapor for a substance that's in the gaseous phase, but more commonly exists as a solid or a liquid. So iodine, for example, has the ability to sublime, where iodine in the solid state can form iodine in the gaseous state, and we refer to this as vapor because it more commonly exists in a solid state. And you can see that process known as sublimation, and we'll take a look at that in a few minutes. Vaporization or vaporization and vapor pressure. So vaporization, again, is the process by which a liquid is converted to a gas. The pressure that the gas exerts on the walls of the container is known as vapor pressure. And we're going to take a closer look at vapor pressure. As I mentioned, this is a term where the substance is in the gaseous phase, but it more commonly exists as a liquid or a solid. You'll see that the molecules at the surface have enough kinetic energy to overcome their intermolecular forces, and they're going to fly off in to the gaseous state. And we're going to take a look at that in the following regard. Shown here are water molecules in the liquid state. You can see the bent water molecule design. Some of you are very confused in regard to water, which is astonishing. Water, of course, is O linked to 2 H's with 2 lone pairs on the O, giving it a bent molecular geometry. Be very careful there. Some of you in your lab, I don't get it. Careful, careful. I'm hoping it just was like a careless boo-boo. So here are your water molecules, and now what's going to happen is some of the water molecules will fly off as they have enough kinetic energy to break their IMFs and go into the gaseous state. And then the pressure that those gaseous water molecules exert on the walls of the container is known as vapor pressure. What I also want to show you here is right now vaporization rate is greater than the rate of condensation, but at some point the rates of these two processes will be the same and equilibrium will be attained. Greater intermolecular forces in the liquid state versus the gaseous state. We'll talk more about cooling the body and cooling any type of substance essentially, but the easiest example is when you're working out really sweating and you get that cooling sensation, and we'll talk about that process in the thermo chapter. But again, you know that liquid to gas is going to be an endothermic process. What's a little confusing, and you guys said, oh, but the temperature's going up. What can be very, very confusing is when you look at the change in temperature for endo versus exothermic, it's not going to be what you think, and we'll get to that in the thermo chapter. So vapor pressure, again, is the pressure that the gas molecules are going to exert on the walls of the container. And you can see the process. Again, we looked at it more in a simulated fashion. You can graph it as well. We'll get into this graphical analysis in the equilibrium chapter. You won't see that at this stage of the game. So the pressure exerted by the vapor when it's in dynamic equilibrium with the liquid at constant temperature is known as vapor pressure. This is dependent on the liquid as well as the equilibrium temperature. What's absolutely critical is that you understand the link between vapor pressure and IMFs. So the time it takes to reach equilibrium, that is where the rate of condensation and vaporization are the same, is dependent on the volume. Smaller volumes will have an increased rate at which that equilibrium is reached, and that's because you have fewer particles. The greater the surface area, that also is going to result in an increased rate in which equilibrium is attained, because you'll have more positions where the particles can leave the liquid state to the gaseous state. As you increase temperature, you'll see the vapor pressure of liquids will increase, and you can plot this with a vapor pressure curve, and that's what we're going to look at in this particular schematic right here. We're going to look at pressure in torr versus temperature in degrees Celsius. 760 torr is 1 atmosphere or standard pressure. Along the line is where the equilibrium exists, and we've got diethyl ether, ethanol, and water. And we've got to do a comparison here so you can see what they actually look like. We have diethyl ether. Now they could not just give you diethyl ether anymore. They would have to, at the very least, give you a chemical formula. Otherwise, you wouldn't know what it looks like. There's diethyl ether.
Can you have just ether?
Ether is a functional group per se, so an ether is going to have O doubly bonded to some R groups. They can be methyls, they can be ethyls, they can be propyls, they can be whatever.
Yeah, church beetle ether.
Don't be fresh. Here's ethanol. Thought you guys liked each other.
We do, that's why we make fun of each other.
Okay. Here we go. Those are the three substances. I'll come back to them in just a sec. Water has the highest boiling point. You can get the boiling point by looking at standard pressure. Water boils at 100 degrees Celsius, ethanol at about 78, and diethyl ether about 35. Why does water have the highest boiling point? Strongest IMFs. Well, let's take a look at that. Diethyl ether is what type of molecule? Definitely polar covalent. You've got a bent, you've got a bent, you've got a bent. Bent things are not symmetrical. Careful. Anytime you have bent, you're going to have a polar covalent molecule. So this is polar covalent, and therefore it would have LDFs and what? Dipole to dipole interactions. No, I didn't.
I didn't know that.
All right. Here's ethanol. Ethanol is also polar covalent. This has LDFs, dip to dip, and it has hydrogen bonding capability because this hydrogen right here can hydrogen bond with
Water.
what other ethanol molecules, etc., because you only have ethanol.
No.
This does not have an H capable of hydrogen bonding because the H's are all linked to C's. Now with water, water is polar covalent as well. So it's got LDFs, dipole to dipole, and hydrogen bonding capability. Which has greater hydrogen bonding capability? Water, it's got two hydrogens capable of forming hydrogen bonds. Alrighty. As a result, water will have the highest boiling point of those listed. So, hang on. They're all polar covalent. These two have hydrogen bonding capability. This one has greater hydrogen bonding capability. Yes, ma'am.
Okay, so say you have two other molecules that form to both of those hydrogens. Can they also connect to make a circle?
Possibly.
Is that gonna make it explode or something?
You'd have to draw me exactly what you're thinking.
Oh geez.
Can you move your drink away from the Chromebook before? Yeah.
I'll just close it.
Yeah. Definitely close it. Thank you.
You're welcome. So cause oxygen, that's not what I meant. Water, has the two H's, so you could have two things, bond to each one through a hydrogen bond.
Well, water, you've seen what water can do in that tetrahedral arrangement. You saw that with hydrogen bonding last time.
Little rings.
Oh yeah, so it'll just make a
Yeah.
circle. Okay.
But it doesn't explode. All right. Now, water has the highest boiling point of those listed. Vapor pressure is the pressure that the vapor exerts on the walls of the container. When you consider water, for example, and you compare it with ethanol, which one requires a higher temperature to boil? Water. So, if you are at 80 degrees Celsius and you were comparing these two substances, which substance would have more molecules in the gaseous phase, ethanol or water at 80 degrees Celsius? Ethanol, because it has a lower boiling point. You've hit its boiling point, so now you'd have a higher percent, if you will, of ethanol molecules in the gaseous phase than water molecules in the gaseous phase because water hasn't boiled yet. So if you have more ethanol in the gaseous phase compared to water at 80 degrees Celsius, what has a higher vapor pressure? Ethanol. So what you're seeing there is with greater IMF strength, you have a greater boiling point, but you have a lower vapor pressure.
Just because of the IMS.
Exactly. All because of the IMFs.
What if you raise the temperature and it goes to the water boiling point?
Let's take a look at that. That's an excellent question. So if you're looking at your graph here and you're at, say, 30 degrees Celsius, which is right here, and you're considering vapor pressure at 30 degrees Celsius for water, you'll see it's the lowest, then ethanol, then diethyl ether. If you look, for example, at 50 degrees Celsius, you'll see water is less than ethanol. So you can pull it right off the graph.
Why is the boiling point higher?
You tell me. In order to boil, you're going from liquid to gas. In order to go from liquid to gas, you have to break the IMFs, and the molecules have to move apart from one another so they don't reform very much. You'll always get some reformation. But, so you have to break all those IMFs to boil.
So because water has stronger IMFs,
Fewer particles will be in the gaseous state, thus exerting lower vapor pressure, because if you consider PV equals nRT, I'm going to flip the screen. What do you know about the relationship between pressure and moles? It is definitely direct. If you move n over here, you would be dividing. When you divide variables, they are directly related. So with stronger IMFs, you have fewer gaseous molecules, and as a result, the vapor pressure is lower. Yes, yes? Very important concept. You can easily calculate the vapor pressure. There's nothing new here from what you learned in your gas chapter, but this is a good link to make, because one thing you will see in May is no part 2 question is going to be about a single concept. Even the itty-bitty questions will involve multiple concepts. So here is a link now between intermolecular forces and gases. So what you can do is you can calculate vapor pressure using PV equals nRT. You've got a 335 mil sample of bromine vapor with this mass. It's in equilibrium with liquid bromine at this temperature. Calculate the vapor pressure. Now in this particular instance, I didn't use PV equals nRT because the mass was given, and simply by dividing the mass by the molar mass, I could get moles. So here's the mass. Be careful in regard to the molar mass of bromine. It's diatomic, so it's about 2 times 80 or about 160. R. The other thing you have to be careful with is the temperature, of course, in Kelvin, and the volume in liters. But there's nothing here that you haven't already done. Very straightforward. As we said previously, when the intermolecular forces are weak, for example, if you only have LDFs, the molecules escape to the gaseous state before equilibrium is established, and now the vapor pressure is very high because you have more particles in the gaseous state exerting pressure on the walls of the container. These types of liquids are referred to as volatile. A kid who has a volatile personality will just snap. They'll just fly off the handle. Same thing with a volatile liquid. You've used some liquids that are volatile. If you've ever cleaned with ammonia, when you open the bottle, you'll be like, whew, just stinks. Hydrochloric acid that's very concentrated too. You'll see it. When you pump your gas, gas contains a lot of octane, which is C8, H18, a nonpolar covalent substance with LDFs only. You can see the fumes or the vapor when you are pumping your gas. Same thing there. Volatile liquid. A non-volatile liquid is one in which the IMFs are very strong, so the vapor pressure is low. For example, water. So vapor pressure is very much linked to IMF strength. It works in the reverse fashion of boiling and melting. Be very careful there. It is commonly asked. For example, no. Where'd it go? Where's my temperature sidebar?
It's right there. Dr. K.
Where?
Go up.
Oh, duh. Those didn't come out so well. That's better. So here's pressure versus temperature for methanol versus ethanol. And now what you can see, for example, which one has a higher boiling point? Ethanol. How come? So you know what ethanol looks like, right? Here's ethanol. And methanol is similar, except you have a methyl group instead of an ethyl group. So they both are polar covalent with LDFs dip to dip and hydrogen bonds. So what type of comparison would you be making?
Ethanol has, you have to break more LDS.
Yeah. Ethanol has more electrons, it's more polarizable, so it'll have more LDF force, if you will, hence the higher boiling point. So if ethanol has the higher boiling point, which has the greater vapor pressure? The other one has weaker IMFs, and that's what you can see here. So if you look, for example, at 60 degrees Celsius, you can see that methanol is going to have a higher vapor pressure. But that wasn't actually the little guy I was looking for. I don't know where it went.
It's right there.
Oh, actually, I think it's here. It's here. It's with this little guy. We'll come back to this in a sec. We're not there yet. All right, and that's actually where we're going. So in regard to changes of state, these are simple experiments that you can run in the lab, and I used to have the kids do it, but they said it was so boring. A heating curve is going to represent a change of state, and essentially what you're doing is you are going to plot temperature versus time, where energy is added at a constant rate. So what we would do here is that I would freeze cups of ice water with thermometers in them or beakers, and then we would heat them very slowly, and we would measure the temperature over time. And shown here is a heating curve, and you probably generated heating curves before, maybe in middle school. You probably saw it in owner's chemistry, or should have. Again, temperature versus time. Here's ice, so that's water in the solid phase. Here's ice and water coexisting, so this is going to represent melting. And then if you trace back on that plateau, you have the melting point temperature. Here's water in the liquid state. Water and steam coexisting, so this would be your boiling point temperature for water is 100 degrees Celsius. And here's water in the gas phase or steam. How come steam burns much more severely than boiling water? It is hotter, has a higher temp, right? How would you compare IMFs between solid water and liquid water? The liquid water has fewer IMFs and steam has essentially none. So what you're seeing here is written out. It says energy flows into ice. Random vibrations of water molecules will increase as the temperature rises. The molecules become so energetic that their lattice positions are broken away from, and now you get the solid to liquid transition. You can see the plateau. Whenever you have a change in state, you have a plateau. That is, the temperature change is constant. Delta H of fusion is the enthalpy change that occurs at this melting point. We'll come back to this concept in our lesson on thermo, so you're not going to see anything about delta H of fusion in this chapter. The boiling point is at 100 degrees Celsius. Now note, this plateau length is greater than this one. It takes a lot more time to transition from the liquid to gaseous state than from the solid to liquid state. Why? Is there a gross difference in IMF formation between solid and liquid? Not huge. But what about from liquid to gas? Yeah, you're breaking them all at that point. So they're all breaking, the particles are flying away from each other. It's going to take a lot longer to break all of those IMFs there. Again, melting, the melting point can be determined where the temperature is constant. Delta H of fusion is the enthalpy change that occurs at the melting point, so the delta H of fusion will correspond right here. The delta H of vaporization will correspond here. We'll come back to that concept in our thermo chapter. Boiling, again, we've actually been through all of this. You can identify unknown substances based on their boiling point. That can be helpful in crime scene investigations. This too is really quite interesting. Atmospheric pressure is lower at high altitudes. For those of you who have ever been to Denver or really any part of Colorado, you've got higher altitudes there in that mountainous region, and atmospheric pressure is a lot lower. Food cooks differently there. You're going to get lower boiling points when pressure is lower. You know pressure and temperature are directly related. And so if they ever have any cooking contests in that area, they very often will have chefs come earlier because they have to get used to food preparation there as compared to, for example, in New York City where a lot of the competitions occur. There is a very interesting section in your textbook on this. I would give it a look-see. If you want to have story time later, I can read it through with you, but I'm sure your level of reading comprehension is considerably better than mine. And I would take a look at that. It's quite interesting. If you watch any of these cooking shows, except probably Worst Cooks in America, they very often use these pressure cookers. Pressure cookers are very useful in cooking food very quickly. When you cook under such high pressure, you essentially increase the boiling point, and now the food will cook much faster. Don't know if you've ever used a pressure cooker. It's not that easy. There's a lot of adjustments that need to be made in your cooking. That's probably why you only see it on Iron Chef, because they know what they're doing.
People make bombs with pressure cookers.
Yeah.
That's interesting.
Yeah. We can, yeah, you can show me your data there. Alrighty. Condensation, you know, is the reverse process of what?
Evaporation.
Or vaporization. So condensation is the reverse of vaporization. It's going to be exothermic, and we will get into these types of calculations in the thermo chapter. We're not going to play with it here. You won't see any questions like that on your quiz, so we'll let it go. Freezing, you know, is the reverse process of what? Melting. You can calculate freezing point the same way you do melting point, but this time you're going to generate what's known as a cooling curve. We don't really do much with this anymore, so we're just going to let it go. My axis got moved. I got to move it back. We're not covering colligative properties. That's why your solution chapter is going to be so empty. And sublimation we had mentioned as well. We'll calculate deltas H's of sublimation in our thermo chapter, so we're not going to worry about that. We mentioned deposition. What we want to do now is analyze phase diagrams. AP Chemistry assumes that you learn this in Honors Chem. I'm not sure you all did, so I do want to just go over it. Don't really think you'll see a question on it in May. I put one ridiculously easy question on your quiz to keep you honest, but I think we'll cover that question right now. It's really, really pretty easy, but it's useful. So with phase diagrams, you're going to have some type of graph in which you've got pressure versus temperature, but what's cool is you can see all three states of matter, solid, liquid, and gas, always in these three positions. So if we were to look at a phase diagram, in green is the solid region, in blue is liquid, and in yellow is gas. And this should look familiar to many of you. As you go from solid to liquid, you've got melting. So all along here, you've got melting. And where the pressure is standard, that is 1 atmosphere, or 760 millimeters of mercury. Some substances are a little different. We'll point that out in a minute. You would trace across and you would get the melting point. Liquid to gas, the transition is boiling. So here's crossing this line here represents boiling. If you go from solid directly to gas, you've got sublimation. And I especially like this diagram because it shows you the molecular details. This is going to show you carbon dioxide, solid. You see the vibration, liquid. So some IMFs still exist.
Wait, what's liquid carbon dioxide?
Well, typically you think just in terms of dry ice, so you're thinking typically solid directly to gas, but under certain conditions you can generate a liquid, but you'll see that region's very small on the curve. Here's gaseous CO2, no IMFs, particle arrangement, very disorganized, bebopping around, sort of like when the bell rings. And this is very cool because this is the triple point where you have all three states coexisting. And those three states are in equilibrium, as you can see those transitions occurring.
Well, like going in and out.
Right here you've got melting where you've got solid to liquid. Here you've got liquid to gas. Now along this line here you have both states coexisting, but when you reach the critical point and surpass it, you don't have two states of matter anymore. You have what's known as a supercritical fluid. What's illustrated here is the sublimation point is going to be at negative 78.5 degrees Celsius. Here's going to be your boiling point right here. No, I'm sorry, your melting point, and then your boiling point, and then you'll surpass. And that critical point you can see right here. This is 10 degrees below the critical temperature, and you can see liquid versus gas, two distinct phases. As you get closer to the critical point, those phases are going to look much more similar until you only have a supercritical fluid. So in regard to a phase diagram, I can ask you any type of silly question. For example, as you go from this region to this region, you would be melting. From this region to this region, you would be boiling or vaporizing. From here to here, if there was an arrow, you would be subliming. If you went here to here, you would be freezing. This is the triple point. This is the critical point.
Is a supercritical fluid a gas?
Supercritical fluid has properties much more, it has properties somewhere in between a liquid and a gas. It's like a blending.
But, like, does it take the shape of its container? And, like,
I don't know. Look that up.
alright.
It's a different state.
The other thing I just want to mention is in most phase diagrams, you'll see that solid to liquid slope of the line right here being positive, but for water it actually has a negative slope. And that's due to the fact that with water, remember in water it's one of the few that expands as a solid. And so the density of solid water is less than that of liquid. That's why ice floats. Triple point I mentioned, critical point I mentioned, critical temperature, the highest temperature at which you can coexist in those two states, critical pressure, essentially just critical point corresponds to both of them, and then supercritical fluids. Shown here for carbon dioxide, as we already took a look at, and those are your phase diagrams. You might see one ridiculously easy question in regard to multiple choice, so you do want to know how to interpret a phase diagram. I don't foresee you having any difficulty with that. Many of you saw the heating curves last year, but you also want to be able to understand positioning, and that was the last thing that I wanted to show you. This is what I was looking for earlier. So what you have here is you're adding heat to a certain amount of liquid, slightly above its melting point, and you're going to see the increase in vapor pressure with increasing temperature. So what you're looking at right here, this is the temperature at which ethane boils. This is the temperature at which ethanol boils. Why does ethanol boil at a higher temperature? So again, here's ethanol. Ethane, instead of this OH here, you would just have an H. So why does ethanol boil at a higher temperature than ethane? Because ethanol has stronger IMFs in the form of LDFs, dip-to-dip, and hydrogen bonding capability, whereas ethane has only LDFs, takes a higher temperature to break all of the IMFs of ethanol, hence the higher boiling point. And that's what you're looking at there. So you want to understand the heating curve, how to interpret it very briefly, vapor pressure versus temperature in terms of IMFs, and it really appears to me that your level of understanding there is pretty high, which is good. They absolutely, they meaning the AP Chem writers, love this big idea. They think it's critically important. You'll see several multiple choice questions. I think they're really pretty straightforward. In terms of your part 2, you've got to be able to explain. Anytime you're talking about boiling, melting, or vapor pressure, your explanation must involve intermolecular forces. Other types of part 2 questions, again, you want to be very familiar with this chart. That's why I made it for you. You want to know the difference between network covalent solids and metallic solids, why these have much higher melting and boiling points than anything else. So those are the things you're really looking at. Make sure you can explain. To help you a little bit better, I'm going to give you 2 additional tools today. We're going to hook to AP Insight. Be careful because that's not your period. And we'll get you signed up for AP Insight in a few minutes. And I'm also going to give you some review books that we purchased for you so that you have more resources to use for multiple choice and part 2 like questions. Those review books go by Big Idea, and we've just about killed Big Idea 2 now, so that's the section you could easily work in. Questions?